Right then, simple harmonic motion. What defines simple harmonic motion? If I asked you imagine a magical bouncing ball with 100% efficiency, and I dropped it from say a meter and it bounced up to a meter and it carried on forever, would that be simple harmonic motion? Yes or no? I'm not going to tell you the answer yet, I will at the end, but just something to think about. How do we define simple harmonic motion? Okay, so if we start with a graph, so let's say you have a pendulum, and the pendulum starts at maximum amplitude. It then swings to equilibrium, goes to negative maximum amplitude, back to equilibrium, and then back to its starting point. Okay, what might the graph of displacement time look like? Well, it starts off at a maximum, goes to equilibrium, goes to a negative maximum, back to equilibrium, and back to its start point. That should, if I draw it well, look like a cos graph, badly drawn. Okay, so we know that x is proportional to cos theta. We know that theta is related to angular frequency by the equation. Angular frequency is the rate of change of the angle, so theta over time. So we can replace our theta with omega t. What's the proportionality constant? Well, what's the maximum displacement? It is the amplitude. So our displacement is equal to a cos omega t. Okay. Now if I look at my velocity, okay, well, at maximum amplitude, our velocity is 0. So I can plot 0, 0, 0 for maximum amplitudes. In equilibrium, our velocity is going to be a maximum. Okay, so what might my velocity look like? Well, as it's moving from right to left, our velocity is towards the negative direction. So our velocity is a negative maximum. And when it's moving into the positive direction, it is going to be a positive maximum. So what graph do I have? Minus sign. Well, let's prove that. So we know that x is a cos omega t. We know that velocity is the rate of change of displacement. So if we differentiate this with respect to time, we are going to get a times, well, wt differentiated is just w, so my omega pops out. Cos differentiates to minus sine, so I end up with v is minus omega a sine omega t. And we can clearly see we've got a minus sine graph. Now looking at acceleration, well, acceleration at equilibrium is 0 because there is no restoring force. When our acceleration is at a positive maximum, the acceleration is towards the negative side. So it starts with negative maximum acceleration and finishes with negative maximum acceleration, and as it moves from the negative amplitude towards equilibrium, the acceleration is a positive maximum. What graph do I have? Minus cos. Well, again, we know that v is minus omega a sine omega t. Acceleration is your differential of your velocity with respect to time. So let's differentiate. Again, we've got a chain function. So we've got minus omega a times the differential of omega t with respect to t, which is omega, times the differential of sine, which is cos. So I end up with minus omega squared a cos omega t. Now, what do you notice? You would hopefully notice a cos omega t is x, our displacement. What have we proved about the relationship between acceleration and displacement? A is proportional to displacement in the direction towards equilibrium. Always. That is the defining characteristic of simple harmonic motion. So pendulums and mass spring systems, the greater the displacement, the greater the acceleration, and that acceleration is always directed towards equilibrium. So we revisit the bouncing ball. Is it simple harmonic motion? You might have been thinking yes, but is the acceleration dependent on your displacement? No, because your acceleration is constant. It equals g. It is equal to 9.81 towards the centre of Earth, and therefore the acceleration is not proportional to its displacement from the ground. So it is not an example of simple harmonic motion. And in deriving this result using differentiation, I'm hoping that has boosted your understanding of the fundamental principles of simple harmonic motion. I hope that helps. Let me know in the comments if there's anything else you'd like me to cover, and I'll see you next time. Cheers.